Hello, I'm Ruth Beyes, Application Technology in Industrial Specialities Division. I'm so sorry that my colleague Pablo Garcia can't be with us today, so I'm going to be your host. Welcome to the Z&S School, the chemical webinars of Zschimmer Schwarz, Spain. Today, we are going to talk about common problems and chemical solutions in water treatment. For this, we have Dr. Carsten Rudolph, PhD in chemistry. In 2002, he joined to the phosphonate division of Zschimmer Schwarz Mosdorf as head of application technology. Since 2019, he has been the head of application technology for Industrial Specialities Division and global head of phosphonate products for Cleaning Specialities Division. Remember that if you have any questions, you can write them in the chat. When the presentation is concluded, we will answer them. So, Dr. Carsten, it's your turn.
Yeah, thank you, Ruth, for having me. Thank you for the entire team of Z&S Spain in Villarreal. Today's topic is basics of chemical treatment, as you called this already, and this is a huge topic, so it's almost impossible to cover all, but I will try to give at least some ideas from things which touch our belongings. So just some words about the history of Zschimmer Schwarz in general and our production site. So Zschimmer Schwarz was founded already in 1894 in the area of Chemnitz. And this is our symbol here. ZS is obviously for Zschimmer and Schwarz. And Chemnitz stands for CH stands for chemistry, not, but for Chemnitz, which is the area here in Saxony. And we produce a lot of chemistry, and the main focus in our production plant is phosphonates. So this is a view on the production side. It's located in lovely green valley. We have a production building where all the synthesis done, a lot of storage facilities, of course, and the R&D building behind. So just to give an idea about the area where phosphonates are produced, and to give an idea what do we speak about, to have the nomenclature a little bit. So phosphonates, in general, there are three ways to describe chemistry. So for example, phosphonates can be simply the salts out of the phosphonic or phosphorus acid. So potassium phosphonate, for example, is a very famous fungicide. It can be also the esters. In some nomenclatures, phosphonates are called also for esters, but these esters are used as flame retardants, for examples. What we produce in our plants, in Mosdorf especially, are phosphonates. That means the salts out of phosphonic acids. And one application field is, for example, water treatment. And in fact, the first phosphonates which were produced in our plants was in 1983. And the first material was in water treatment chemical. So there is quite a long history. If we want to compare the phosphorus-based chemistry, so we can compare the phosphonates itself with the phosphates. So phosphates, the most simple form, phosphoric acid, which is quite well known. By condensing this, one comes to the pyrophosphate, and former condensing to the polyphosphates. And in fact, these polyphosphates were the first material to treat scaling, to inhibit the formation of incrustations. This works quite well, but the phosphates, the polyphosphates, are sensitive against hydrolysis, and in contrary to this, phosphonates are much, much stronger due to the bound where this functional group is connected with the backbone of the molecule. So I would call phosphonates the better version out of the polyphosphates, so to say. In fact, we have from this series of antiscalants, we have 4 basic properties. And the first one is chelation or sequestration, followed by hardness stabilization. That means the prevention of incrustation. Also dispersion or deflocculation is of importance, and corrosion inhibition or passivation. So when we speak about complexation or sequestration, this is a topic which is not touched that much in the traditional field of water treatment, but it is more important for cleaning application. Here we touch reverse osmosis, the cleaning intervals, for example. Dispersion, in case of dispersion, we have the prevention of a mud which sticks on walls. Here the point is to keep the material flowable in order to get rid of it during the cleaning steps in the systems. I think by far the most important property is the hardness stabilization, also called as threshold effect. Here we have the prevention of incrustation, which is illustrated here with this small heating device from the kitchen, which is incrustated with chalk. And here the inhibitors perform in very, very small amounts. The chemists call this in substoichiometric amounts. Last but not least, we have the corrosion inhibiting properties. Corrosion inhibiting, or I would call it rather a passivation, because this kind of chemistry acts mostly as an anionic inhibitor, as an anodic inhibitor, and this is rather called an passivator when a corrosion inhibitor. But for a lot of applications, this plays an important role if we speak of cooling water treatment, for example. If we compare with chemistry, so there are a lot of raw materials around which are used to produce chemistry for water treatment. Then we have, for example, the classical chelating agents. So chelating agents, if we compare with basic properties like sequestration, NTA or EDTA, of course, these are known as chelants. So we have the highest performance here in this spider diagrams. We do not have any hardness stabilization because they do not work in substoichiometric amounts, only in stoichiometric amounts. And we also do not have any corrosion inhibiting property because they form always soluble complexes and would steal the iron out of a metal pipe, for example. There's also no dispersing effect, but they are stable. So in fact, the performance portfolio, if you want to call it like this, of EDTA or DTPA looks like this. So they are known as sequestering molecules. So if we speak about polycarboxylates, so that means polyacrylates or polymalleates with high molecular weight, then we do have, of course, the dispersion effect. So polymers are known for its dispersion properties. We do not have any sequestration because no formation of chelates, simply due to the size of the molecule. We have some hardness stabilization, surfaces are covered, and also a little bit of corrosion inhibiting properties. From the hydrolytic point of view, I think it's not that stable in comparison to EDTA, but it is rather stable. So an overall performance portfolio could look like this spider diagram here. If we speak about the inorganics, the orthophosphates, the salts out of the phosphoric acid, then it's clear corrosion inhibiting. This phosphating is the effect we can only address here. So this is a rather small performance portfolio. In contrary to the polyphosphates, polyphosphates are indeed also some kind of multifunctional products. So we have some hardness stabilization. So Calgon, the first series of this hardness stabilizers were based on polyphosphates. And we have also some dispersing or passivation effects. I think the most weak point is the hydrolytic stability, and for this reason, there's always necessary to give an excess into the system. And this was the reason why in the late 1980s, for example, the polyphosphates were banned from the detergent market due to the formation of eutrophication, or due to the reason to cause eutrophication in surface waters. In contrary to this, phosphonates show a little bit of everything, I would say. Phosphonates are strong sequestriants, so the chelation power is absolutely in the range of NTA or EDTA. Phosphonates are the leaders of hardness stabilization. This is a key property. We have some passivation properties and also some dispersion properties. So this shows that phosphonates can be used in a wide range of application, but this also proves if a service company intends to build a formulation and anti-scalant, mainly one uses different chemistry, combines it, and for example, if you want to do this with a phosphonate and a polymer, then we can create a product which exhibits a nice hardness stabilization and also a nice dispersion. So this is state of the art, and the reason for this is the different properties of the individual classes. If we want to understand a little bit better how this chemistry works, I picked from these 4 basic properties this property, which is, in my opinion, the most difficult to understand. And this is the scaling inhibition. Phosphonates are also called as threshold inhibitors because they act in substoichiometric amounts. So the ratio we can get under controlled conditions is in the range of 1 to 10,000 approximately. That means 1 phosphonic acid can treat up to 10,000 calcium ions. And this is hard to understand, even from the steric point of view, but there are reasons behind. So one reason, also most important one, is that we do not speak about a chemical reaction here. In contrary to chelation, we have here an adsorption, which is more a physical property. So that means we need already a crystal out of an alkaline earth metal, for example, could be calcium carbonate, and then the inhibitor adsorbs onto the surface. And due to this adsorption onto the crystal surface, the growing of this crystal is retarded. And if the adsorption takes place in very early places, then the crystal will dissolve with the time. And so we then have an dissolution of the crystal nucleus, or the baby crystals, or the clusters, however you want to call this, in this very early stages. And the phosphonate, or the inhibitor in general, is free to adsorb onto the next nucleus. So we have some kind of a step-by-step mechanism. And this explains why we only need a very small amount of inhibitor to treat huge amounts. So, of course, it is to understand that even if we treat this nucleus or with clusters, there are always crystals which will come to the adult stage. So, and in this case, we have an adsorption on the regular crystal surface and an interference with the crystal growth. And as a result, we have a precipitation of distorted, of small crystals, which can be easily removed in the mud, which is of key importance for cooling water applications, for example. So the main point here to understand the effect is that this hardness stabilization works completely different to sequestration. Sequestration is chelation in stoichiometric amounts, 1 chelant, 1 metal ion, and hardness stabilization in the substoichiometric amount. So this explains quite well how this works. Of course, the desired course is always to run the system into this area where we have this step-by-step mechanism, and to keep the crystals in the small size. So if we speak about hardness formation or about this chalk formation, everything is about crystallization, because crystallization is the key to form these encrustations. So it makes sense to understand how this crystallization works. So the necessary condition for crystallization is any supersaturation. So crystallization takes place on areas where we have supersaturation. The supersaturation can be driven by different forces. This can be by evaporation, so something of thickening, for example, also change of temperature. If you remember on this heat exchanger, it's the hot spot in the system, and at the hot spot we have this chalk formation. And there are a lot of parameters which influence the crystallization process. So this is, for example, the degree of supersaturation. Of course, this is obvious. The higher the supersaturation, the higher the probability for crystallization. Other properties are not that obvious. So the induction period or the tendency of supersaturation or nucleation, even crystallization speed is a typical property of different matters. So one material crystallizes fast, the second one crystallizes slow. This all influences the crystallization process. And last but not least, in practice, we are confronted with the specific system conditions. So the mechanical stress, any diffusion conditions, or even background electrolytes will influence the crystallization process. So what I want to say here, this is hard to predict. One needs experience in order to understand these fundamental properties. Just to visualize a little bit and to make it more obvious. So this is an aqueous system. Within our aqueous system, we have the dissolved ions, so the calcium ions and the carbonate ions. And upon the point we exceed the solubility levels, both will combine to calcium carbonate. So calcium carbonate is a dipole. Here we have the cationic part, which is positively charged, and the anionic part, which is negatively charged. And whenever we have some of this calcium carbonate particles, they will adsorb together, and similar to magnets, to stick magnets, they will form any kind of cluster which is not well oriented. So this kind of cluster is from the property similar to the water. So there is no driving force to precipitate. There exists this famous Latin speech, simila similibus solventur, and here the cluster is quite similar to the water, and so it stays dissolved. At any point, the more material comes to this cluster, the higher will be the charge density, and then there is a driving force for the cluster to reorganize. If we meet a room with 2 people only, they can move around as they like. If we add 100 more people, they need to orient in order to get all into this room. And the same is with these particles. They will reorientate to a crystal, and this is the first point where a real crystal exists. And the properties of these crystals are completely different from the property of the aqueous system, and for this reason we have a driving force to precipitate. That means as long as a material can kept in this nuclear state, the higher is the probability for supersaturation, and the less is the risk for precipitation. On contrary, if the crystallization proceeds, then the crystal will grow and grow and grow until a pipe is blocked, for example. So these are the fundamentals of crystallization. If we discuss the application areas, today's topic is water treatment. So, and classical water treatment is, for example, cooling water treatment, it's boiler, it's desalination, either on the thermal way or by membranes. But of course, we have also a lot of other industrial applications, which are more or less also water treatment, because there's an aqueous system which needs to be treated and adapted onto the conditions. But today we want to focus only on the traditional ways of water treatment. And if we speak about water treatment, so water treatment chemistry, what is involved in water treatment chemistry, well, we have, of course, at first the water qualities. The water qualities means the ions which are dissolved, so which is usually described by the water analysis. So we have some different pH, turbidity, any organic pollutions. All this describes the involved water quality. And then in practice, of course, we have the materials which are the equipment is made out. So this is the tubes and pipes or membranes in case of any separation technologies. Basins can be of concrete, for example. If we speak about cooling towers, can be any tanks from high-grade steel or vessels from carbon steels. Heat exchangers and fittings made from copper or from brass. So a lot of different materials. And with all of this, we have to deal, in which will influence, in this case, an water treatment service needs to be done. And finally, of course, we have the process or the physical conditions. So the constant duration time. So depending on the process we speak about, we could have a very short duration time if we think on reverse osmosis, for example, or a rather long duration time if we speak about cooling towers. So this depends on the process. And so in summary, due to the variety of process variables, a general product recommendation is difficult. So it's always recommended to test the specific customer conditions, and the more detailed the information we can get, the better will be the technical recommendation for the treatment of this aqueous system. If we speak about the product requirements in water treatment application, well, this differs from application to application. So I tried to fill in here some application fields. So for example, membrane separation process, as an example, the reverse osmosis for drinking water production. Here, the main topic by far is scaling inhibition, of course. Chelation does not play any role for the continuous dosing of the antiscalant. It does play a role if we speak about the cleaning intervals. For the cleaning chemistry, chelation is of importance, but not for the treatment of the feedwater. Dispersion is of importance, of course. Corrosion inhibition, nothing, so it's made of plastic. And of course, if we produce drinking water, there are also some approvals. The approvals differ from country to country, but there are also some approvals which are international. So NSF, for example, for this reason, also some of our products, and Kublen is the brand name of our phosphonates, are approved according to the NSF Standard 60, which is a US-American drinking water standard for using chemistry for the production of drinking water. There are other parameters of the product which are of importance. So one is, for example, the calcium tolerance. That means the tolerance against high calcium content, which is of importance for this membrane separation processes, because here we have also, if the duration time is short, but the concentration ratio is incredibly high in front of the membrane, so it plays a role. Stability or decomposition is not of any importance here because the duration time is extremely low. Also, solubility or pH does not play a role because the dosage is extremely low, a few ppm only. If we speak about heat exchange systems, we need to differentiate between open systems and closed systems. If you speak about open systems, then we have, for example, cooling, which is applied by evaporating water. So, and for this, we have the scaling inhibition as a very strong impact. Chelation does not play a role, but dispersion, corrosion inhibition, because we have different substrates. We have steel from the pipe, we have from the heat exchanger, the copper or the brass. So for this application, usually formulations are used, and these formulations are mixtures which show properties which are useful for this application, ideally already together with corrosion inhibitors. For boilers, for example, if you speak about boiler water, one example would be the steam production. Steam production depends on the quality of raw material which is used. If a demineralized water is used, then scaling inhibition is not of interest. Then it's only the corrosion inhibition, and the scavenger is necessary, for example. If a standard water is used, then scaling inhibition could be of interest. In closed systems, the scaling inhibition is not of importance because the system is closed, no evaporation is. It is simply in brackets an exchange of temperature, and here mainly we have dispersion of any particles which are in the system, and of course corrosion inhibition. Corrosion inhibition is the most important point, and sometimes here formulations are used which mainly consists of passivators for different chemistry, could be phosphonate, could be amine, could be even a molybdate, depending on the area and on the local regulations. So different possibilities are here for this closed systems, mainly in heating systems. And last but not least, something more exotic one, the energy production by geothermal sources. So geothermal energy, especially in Germany, for example, we have some areas where we have the first tries to produce energy out of an aquifer, which is in the depth of approximately several hundred meters with a temperature of 150 to 250 degrees in Celsius. And here some more exotic scales occurs. So the conditions are different. So we have a limited oxygen entry. So corrosion is special, and also the salts which tend to scaling are special. So barite, for example, barium sulfate is very famous for this. And here we need some special scale inhibitors. So that means for each of these processes, we have different requirements in order to fulfill the requests we get from this application. Boiler water treatment is the first example I want to discuss a little bit more detailed. At least in our area, this boiler water treatment is not of that importance anymore because mainly demineralized water is used, so scale inhibition is not that huge topic. It is corrosion inhibition, so scavengers, oxygen scavengers is the topic in order to keep the corrosion inhibition, the corrosion slow, and also sludge modification. So at the end, it is to maintenance the thermal energy and the thermal efficiency. So this is the main target. And so the products which were applied in the past were standard phosphonates. So today we have mainly oxygen scavengers, which are used here for steam boilers, for example. If you speak about desalination by membrane separation, we have different classes of membranes. The most rough one is the microfiltration. So with microfiltration, particles, algae, and bacteria or suspended matters are filtrated. The second step is the ultrafiltration. Ultrafiltration is for surface water or spring water. And here, beside of the suspended material, already viruses or high molecular substances are separated from the water, and by this the water can be purified. the next finer step is nanofiltration, and in nanofiltration, so there can be the humic substances, pesticides, and also the first polyvalent ions can be separated from the water. The last step is the reverse osmosis, and with the reverse osmosis, even the salts of monovalent ions like alkali or chloride or nitrates can be removed from the water. And depending on the steps, different technologies are applied to keep the system running, and sometimes or even quite often, these techniques are combined. So, for example, in front of a reverse osmosis and ultrafiltration or and microfiltration is applied in order to make a pre-treatment of the feed water. So this depends on the technology which is used. The aim of the application is always to remove dissolved impurities and sometimes to generate some potable water out of the salt water, or to manufacture any ultra pure water for power or for electronic industry. And depending on the needs, one needs some special certifications, the NSF certified products I mentioned already. And in reverse osmosis, for example, we have a filtering process on ionic level. Various filtering implies we have this filter model with a mesh, which is not really true. It's because the latest separation technology following this process is nanofiltration. For reverse osmosis, it's a little bit different, but at the end, the same is to prevent the scaling on the membrane, there, of course, on the pressure side, and to preserve the membrane efficiency, and at the end, to purify also the used membranes, because this is always necessary at the end. In contrary to these membrane separation processes, we have the multi-stage flash evaporators, which we have mostly in areas where electricity is cheap or thermal energy is available. For example, in areas where we have an oil production and thermal energy is present. Here in this area, mainly the multi-stage flash evaporators are used, which is not the case for Europe. If we speak more detailed about reverse osmosis, so the principle is we have a feed water, and the feed water is pressed through a membrane, and by this we produce the cleaned water or the permeate and the concentrate. At the end of the process, approximately 90% of the water is transformed into the permeate, and only 10% remains as a concentrate and is the waste. Of course, this is not possible to do on one step. Mainly, it's a multi-step process. So, for example, the so-called Xmas tree is used, where we have different steps. So, in the first step, we have the first thickening ratio, and then the concentrate is used as feed for the second step, and then finally this concentrate is used for the third step, and at the end we have only 10% of the concentrate left and produce 90% of the permeate. So that means that the thickening increases from the left side to the right side, and for this reason also the nature of the fouling changes. So from organic fouling to inorganic scaling, we have a shift depending on the scaling. So this shows a little bit more detailed how this filtration applies. We have here the static filtration, we have in dynamic filtration where we have a constant layer of the concentration. So these are only two processes. The main important point for reverse osmosis is to stay or to keep this permeate level again to the standard, and this is done by regular backwashing intervals. And by this backwashing intervals, the filtration is recovered, the permeability is increased, and this is done by intervals. And the longer this goes, the more the irreversible fouling will stay on the membrane. And by this, the importance of the chemical cleaning becomes obvious. The better this chemical cleaning is applied, the better it is for the process, because the longer can the membrane stay. This gives an idea how this concentration increases over the time. So this is from the left to the right. The more it is concentrated, the higher is the concentration, and the higher is the risk of precipitation. And this is the scheme of the membrane for this reverse osmosis. So this is not really as a model of this filtering gaps or filtering meshes. It is in polymer. And here the different ingredients, so to say, of the water funneling with different velocity. So the water will funneling with the highest velocity and will enter the permeate area. And the ions, which are much bigger in size, are blocked and stay on the feed stream. This is just for illustration. To get an idea about the thickness of this membrane. So these membranes are extremely thin. They are, for this reason, mounted on a carrier in order to keep some strength to avoid damages. But the active layer itself is really, really thin. So we speak about microns only. In practice, we have different models. So hollow fiber models are used sometimes for wastewater treatments. For a lot of standard reverse osmosis applications, we meet nowadays the wrap models, or called spiral wounded models, where we have a high efficiency and high area of separation on a concentrated space. So this is how this spiral modules look like. The chemical additives we can differentiate into two classes. We have the feed water conditioning, which is a continuous conditioning, and we have the membrane cleaning, which is done via intervals in order to remove the fouling from the membrane and to go to the next cycle of use. The application of chemicals, of course, in total, we have much more, not only the antiscalants, we also have the pre-treatment of the water, which can be mineral acids for pH regulation or any flocculants. So a lot of different chemistry is used in order to keep this process as efficient as any possible. If we speak about cooling water, the situation is different. In cooling water, we have a system where the water circulates, and a part of this water evaporates, which is approximately 30%, and the remaining 70% is cooled down. For this reason, we have a concentrating of the material inside, and an antiscalant is dosed into basin and prevents the incrustation, which mainly occurs on the critical spots. The critical spots is the heat exchanger, because this is a hot spot, and in the cooling tower itself, where the water is sprayed down. And here in the installations, we have this blocking with the chalk. Beside this, we have also a biological treatment, and also corrosion inhibition plays a role. Of course, the costs needs to be looked for. This is the target behind everything. So that means simple working, non-complicated installations are preferred, and the costs for the water treatment needs to be lower than the cost for a possible damage without of the treatment. This is the idea behind. The treatment program contains the scale formation, surface and surface and pitting corrosion are issues which needs to be treated, formation of deposits, and also the algae and bacteria growing needs to be treated. So in fact, we have a complex treatment of all the tasks, and usually a scaling inhibitor, corrosion inhibitor, and dispersion agents are applied, ideally all in all together in one product. Corrosion inhibition, I mentioned already. Different forms of corrosion inhibition are possible depending on the pH. Could be an irregular corrosion or a regular corrosion. So this is really a topic of interest for the cooling water treatment. The deposits we have either the one from inside the system, the high concentration of dissolved salts, and also from the outside. We have the flue dust, we have ash, we have biological foulings, and in biological foulings we have algae, but also microorganisms play a role. So these are the deposits one need to deal with. Dispersing agents in the system, we mainly need to deal with calcium carbonate. Only in random cases there is also calcium sulfate or even phosphate. This always depends on the source of the feed water, and also the selection of the corrosion inhibitor depends on the water. And the more the better the system is maintained, the more efficient can the chemical inhibitor perform within a defined system. Hardness formation, this is something we discussed earlier. What are the driving forces for this precipitation of calcium carbonate? So the impact, of course, is the scale formation on heat transfer surfaces, which is a hotspot, and on the spraying zone inside of the cooling tower, as I showed in the scheme of the cooling circuit itself. What do we provide from the technical side? We focus on quality assurance. We also try to give technical support. So we are equipped in our laboratory with a good range of techniques. We perform different titration techniques. We have capillary electrophoresis in order to analyze products. We operate NMR spectroscopy and ion chromatography, which is useful to characterize antiscalins or products, to characterize the stability, to monitor the efficiency. We have a separate tool where we are able to follow scaling processes under continuous processes. Here we can adjust the conditions from cooling system up to oil-filled conditions with higher temperatures and higher pressures, depending on the current project. And we are equipped for corrosion measurements. I would like to say thank you for your kind attention, and please feel free to ask. I will be happy to answer as much as possible.
Okay, thank you very much, Dr. Carsten. I would like to ask you two questions. The first one is, do we offer ready-to-use formulation or raw materials only?
Yeah, that's a good point. So in fact, we as Zschimmer and Schwarz are basically a raw material producer. We are not a service company. For this reason, we produce the raw materials, and out of this, the different products are produced for different application fields, independent. If we speak about pulp and paper industry or textile or energy production, in each case where we have any water system or aqueous system which needs to be treated. Of course, sometimes we get customer requests, or we have certain projects where we are able to develop a solution, a ready-to-use solution, and of course, these products are then also available for the market. So, for example, for cooling water treatment, we have also ready-to-use formulations in our portfolio, or also for reverse osmosis, we have some experience where we are able to provide more than the only raw material. But in general, That's right. We are raw material producers. That's true.
Okay, thank you. And the other one is, what about the so-called dosage prediction software to calculate the necessary dosage of antiscalant? Do we offer this kind of service?
I think this question is connected with the first one. In chemical industry, you need to position yourself. You need to position, are you feel more like a service company? Then you need to provide the chemistry and the technical support, or are you more in the area of the raw material producer? The point you mentioned with so-called dosage prediction software is quite an interesting point. Also, as we are equipped with a laboratory where we are able to analyze the behavior of chemistry in contact with supersaturated systems, so basically with water treatment questions, we miss one important share to operate this kind of software, because this software is based on both the experience from the chemical point of view, where you calculate how an antiscalant interact with calcium carbonate, for example, and the practical experience from operating the systems, operating a reverse osmosis facility with a defined water quality, with defined installation parameters, with defined membranes. And if you put this together, then you are able to form this kind of prediction software. And this means only a service company which has this practical experience in this in this operational or a provider of membranes, this industry is able to provide this prediction software. We, as a raw material producers, not. We can calculate supersaturations, stuff like this, from the more scientific point of view, with out of brackets. It is scientific point of view, but we are not able to transfer this for 100% to the practical application. This is the job of the service company.
Okay, thank you very much. The time is up, and thank you all very much for participating in the Z&S School. I hope you enjoy the webinar. As we always do, remember that we will send the video of the session to all registered participants. If you have any remaining question, you can always reply to this email. And Carsten, nice to see you again. And thank you so much for this interesting presentation. And see you next month with a new topic. Thank you for us.
Thank you for having me, and best greetings to Spain.
Nice.